It's live. It's live.
We're live?
We're live.
All right.
We're live.
1, 2, 3.
You're listening to Thinkative. Yes, you are. The podcast for philosophers, seekers, and the generally curious. I'm Tim Newton.
I'm Matt Parker.
And I'm the Jace.
And over there we have Gavin.
Running the camera.
The man Ericsson. Yeah. And yes, here we are. After a long absence, it feels 4 weeks. It's been a full month of
It's been 4 weeks.
It's been 4 weeks.
Full 4 weeks.
I
Since
do
we
believe
we
it.
had Brian here on the Joanna, but yeah, tonight is going to be a very sort of, and especially thinkative. I think.
Well, I think it will.
It will be, because
so,
we are
maybe so.
doing what are we doing?
We're going to be talking about unsolvable problems.
Okay, great.
Problems that really cannot be solved.
Great. This is
Not unsolved problems.
unsolvable.
Not unsolvable problems. Yes.
Right,
Unsolvable.
okay.
Unsolvable.
But well, let's get to our solvable wine
Let's do
before we
that.
do that, which is this week. It's an Argentinian Malbec called the Beefsteak Club. Somehow beef and liberty. So no beef, no cows were harmed in the making of this wine, as far as I know.
Right.
But
Now,
yeah.
wait.
Oh.
Before you pour,
Yeah.
I have a request.
Okay.
Could you please
Shut up.
fill my glass? No. That's an unsolvable problem. Could you please fill my glass all the way to the top,
Yeah.
but leave it completely empty?
That's not going to happen, is it? I can fill my glass all the way to the top and leave yours completely empty. But that's the best I can do. Does that sound like the beginning of a seriously unsolvable problem?
Well, I wouldn't call it too serious, but it's all right. Forget the problem.
That is
Just
a
pour some more.
serious. Yeah, that is a serious. If you have to have an empty glass,
I'm
you can't-
curious.
A curious problem.
What
yeah.
the answer is.
There you go. There's some for Jace. Say when.
I went, sorry.
Okay.
Okay, great.
Right. I
Right.
want to know about that then. Can you do that? You can't do that, can you? You
Not as
can't.
far as I know.
No.
No. See, it's an unsolvable problem.
Ah.
That's the idea. Cheers, John.
Cheers. My glass is half full. That's one thing. That's certain.
Oh, God.
Cheers.
Cheers, Gav.
Wait a sec.
Cheers.
But you did say, can you fill the glass to the top but leave it completely empty? Solved it.
Okay.
If you don't factor in time, you fill it to the top, you drink it, when you leave it, it's empty.
Oh, that's excellent. That's really good. So what I meant was
Yes.
leave it continuously empty.
I know.
But that's correct wording, right? You might say leave it empty,
Yeah.
meaning you've left and
away
it's
from
Left
empty.
and it's empty.
Oh,
That's
yeah.
excellent. That's a good solution.
I
That's a very
see.
good solution.
Yeah.
So then that brings up the question, right? Is there really such a thing as an unsolvable problem, or are there just lazy people who give up?
Yeah. Well, I don't know. Do you?
Well, okay. So I know some facts that might enlighten us about this.
Okay.
I know that there are problems in mathematics
Yeah.
that have been proven mathematically to be unsolvable.
Right. Okay.
Right? So according to mathematicians, yes, there are completely unsolvable problems, and mathematicians are often inundated with sort of amateur mathematicians thinking that they've solved these unsolvable problems and sending their work in to professional mathematicians and asking them to read it and saying, hey, look, I've solved this amazing
Yeah.
problem.
Like
Yeah.
for instance. What's
Like,
it?
for instance, well, so I've heard that a lot of people have tried to do things like trisecting the angle or squaring the circle.
Okay.
So these are ancient geometric problems, right?
So squaring the circle. What's that, and why is it impossible?
Squaring the circle is, well, let's start with trisecting the angle actually, because
okay.
that's a simpler one to visualize.
Trisecting the angle.
Trisecting the angle,
Okay.
right? So trisecting the angle is this problem of, so first of all, you have to know the setting of the problem. And I think that's really important to understanding what counts as an unsolvable problem to mathematicians. There are specific rules, and there may be ways to sort of solve the problem in a practical sense,
Mm-hmm.
but they break the rules.
Okay.
Right? So you can't really prove something is unsolvable unless you have a very clear characterization of what counts as a solution. Right? Okay, so for these problems like squaring the circle, trisecting the angle, the main rules are you have to use the methods of Greek geometry, which means you do everything with a compass and a straight edge.
Okay.
Okay, so so I have a compass here.
Right. Okay.
So,
Blimey, I told you this is especially.
I don't mean the kind that points north, right?
Ah.
The kind that draws a circle.
Okay.
Right?
Yeah.
Okay. So, and of course I have here a straight edge, commonly known as a ruler,
Yeah.
but the marks on the ruler aren't going to matter for these problems. Right?
Okay.
So the idea is all we're using is something that can make a circle of any size,
Yeah.
and something that you can use to draw a straight line. That's it. Okay. And the idea is you want to come up with a method to construct certain things with just these two simple tools. Right? And the history of this is supposed to go back to maybe Egyptian or Babylonian sort of agriculture and measuring land. So they would use sort of ropes and stakes
Yeah.
to measure things. And basically you can do the same things with a rope and a stake as you can with a compass and a straight edge.
Yes, I get it.
Right? Because with two stakes and a tight rope, you've got a straight line.
Mm-hmm.
And with one stake planted in the ground
Yeah.
and the other one loose, you can draw a circle.
Okay.
Okay? So the idea is we want to be able to sort of construct things with these two simple tools. And the problem with trisecting the angle is, can I go to the board here?
Over to the board.
Oh, right, go to the board.
Set up some paper here. Right, so the problem with trisecting the angle is, say you've got some arbitrary angle, right? And an angle is just two rays or half lines, right? So we imagine they could go on forever.
I'll tell you what,
Yeah,
bring
one-
it over there, then we'll be able to hear on the mic.
Oh,
yeah.
I might not hear you.
What's that? Bring it over
Bring
here.
your
Bring
thing
it
up
over
there.
here.
Forgot about the mic.
Oh, yeah.
And
Gotta get a lot
then,
near for
you
this
can
kind of
be nearer
stuff.
the microphone.
Right.
Yeah.
Okay, good. Okay. So, and the problem with trisecting the angle is to use a compass and straight edge to draw a straight line and another straight line,
Yeah.
divide that angle perfectly into three equal.
With the emphasis being on perfect.
Yeah, perfectly, right? And of course, you know, I'm just a guy with a compass and straight edge. It's not really going to be perfect, but we imagine that if I could do my constructions perfectly, if I could use this compass and straight edge perfectly, then the result would be perfect. So the method itself has to be perfect.
Yeah.
Okay. So
How do you do it?
well,
you can't do it.
you can't. Yeah, that's it. That's it.
Ah.
But before we come to that, let me
Yeah.
just sort of, just to give you an idea of like what these compass and straight edge constructions are like, right? Things you can do. So say you've got like a line segment and you want to construct another line that's perpendicular to that one.
Yeah.
Okay, so here's how you would do it with compass and straight edge. All right, you can put the point of the compass on your line, and let me make a nice big circle here. Try to make it dark. And you can draw an arc like that. Let me make sure it goes all the way around.
Yeah.
See, it is imperfect, but oh yeah, that's
Yeah.
looking pretty good.
Yeah.
Okay, and now you can just do the same thing with a circle from another point.
Same size circle.
It doesn't even have to be the same size circle,
Oh,
but
really?
it has to have its center on the same line,
Oh, okay.
right? And then you've got 2 points of intersection here and here, and you just use your straight edge to draw a line through them,
And that's bang on 90 degrees.
bang on 90 degrees, right? In theory, if I did everything perfectly, then it would be perfect.
Oh, that's good.
Okay.
All right.
So that's the kind of construction you can do. And you can do the same kind of thing here, right? You could bisect this angle by doing the same sort of thing. Right? Oh wait, let's start like this. We'll first draw an arc through the angle so that we're starting at the same distance on each of these rays.
Okay.
Right here.
Yeah.
Okay. Well, then I have to make it a little bit
And that
larger.
would have to be the same size circle, I'm guessing.
Yeah, in this case, it does have to be the same size circle. That's right.
Okay.
Okay. Okay, and then you just have to draw a straight line through the original vertex of the angle and the place where those two arcs intersect, which is right here. And then you've perfectly bisected the angle.
Okay.
So there ought to be something like that you could do to divide the angle into 3 equal parts, right?
Yeah.
Trisect the angle.
Trisect.
Surely,
Okay.
if we can bisect it, we can trisect it. Right?
Yeah.
But it turns out to be impossible.
Okay.
And people have tried for, thousands of years, and it cannot be done. Now, how do we know that it cannot be done? Well, because people have tried for thousands of years and no one's done it.
And they've still failed to do it. But that's about being very exact, because you can sort of roughly do it, can't you? When
You can roughly do it.
when you're carving up cheesecake.
Well, yeah, you can. Okay, so, but let me just say that I'm just kidding when I say it's because we've tried for thousands of years and no one has done it.
Oh, right.
There are lots of hard problems.
Is that like a mathematician?
If I were a mathematician, it would be a mathematician's joke.
Okay, yeah.
Yeah, I guess that's what Patrick says we were.
Mathematicians. We're not getting at mathematicians. Some of our best listeners are mathematicians, probably.
I would hope.
We hope.
I hope. Yeah.
They're leaving in their troves.
Yeah.
Yeah. Oh, by the way, that
send us a
reminds
message
me.
if you're a mathematician.
That's right, messages. Please do, if you're watching, as we go along here, at 1:30 hour, we're going to have a look at anybody who may have messaged us on Facebook. And we will,
Yes.
because we've been very lax about this before.
Yeah.
Yes,
People have been busily sending us messages, and we've just got...
I'm solving
We're
the
just
social
chatting
media
on.
problem.
Yeah.
Oh,
We're
I'm
going to be
working
on
on
it.
that.
Jace is solving it
I'm
right
doing
now.
social media here.
So
That
we're
is
across
not
it.
an
And
insult.
we want to hear from you. Should you manage to have squared a circle or trisected an angle, especially.
Yeah, send us your work. We'll check it. And and the problem with squaring the circle then is, okay, so if you've got a circle, suppose you've already got a circle. Well, I don't need to draw a circle. We all know what a circle looks like. Supposing you've already got a circle, the problem is to use a compass and straight edge to draw a square that has the same area as the circle.
That's squaring the circle.
That's called squaring the circle, right?
And that can't be done.
And that can't be done either. Now, how do we know these things can't be done?
Because
Well-
we've been trying for thousands of years.
That's not it.
Oh,
That's not
okay.
it, actually. Actually, in the 19th century, there was an algebraist called Galois, and basically, what it all comes down to is it turns out that the things you can do with a compass and straight edge, you can construct all sorts of line segments with a compass and straight edge and angles, but the line segments and angles that you can construct with a compass and straight edge, it turns out, they form a certain set of numbers, right? So if we do this all in Euclidean geometry, so that each point is associated with a pair of numbers, then it turns out that if you start from just a line segment like this one, then the places you can get from there are infinite. There are infinitely many points that you can construct, and infinitely many different line segments you can construct, but you can't construct all of them. All right. So the methods of the compass and straight edge only generate a certain subset of the points on the plane.
Which is why we came up with these, I guess.
Yeah, but that doesn't really help that much, right?
What,
A
protractor?
No,
You could trisect with a protractor, though, couldn't you?
you could.
How
but
did they work that out, then?
How did they work that out? Well, the thing is, the problem of trisecting the angle is you need a method that will work with any angle, so that you can trisect any angle whatsoever.
Okay.
So there might be methods to trisect certain angles, like there might be a method to trisect a right angle into three 30-degree
30
angles.
degree angles, yeah.
But that doesn't mean that you've solved the problem. You can't trisect all the angles that way.
Right.
Okay, so
Oh.
it's a problem of finding an algorithm, finding a method that'll work in any case, for any case that I give you.
Okay.
Right. And the thing about protractors is yeah, they've got these lines on them so you can measure the angles. But how did those lines get there? Somebody had to draw them,
Yeah.
right? And how did they draw them? Well, you'd have to use a method like a compass and straight edge, or some kind of method to determine where those lines should go.
So then this might be inaccurate.
Yeah, well, it surely is inaccurate, just because, you know, everything is. Nothing's perfect.
No.
Nothing that we make, anyway.
Okay. Yeah. How did they? Anybody knows how they make protractors?
Yes.
Let us know.
It's a very long and protracted process.
Oh,
Yeah. Yeah.
Jace.
Jace. Yeah.
Okay.
So, yeah. How? Okay.
He wants some pie.
I want the pie
pie.
because
Okay.
this seems to be working towards it. It's a mystery. This thing about unsolvable problems to me.
So the thing about these problems is, like I said, they're only unsolvable if you specify them in a very precise way.
Right.
If I say to you, cut that pie into thirds, or maybe even if I cut two arbitrary angles in a pie, and I say, now cut that piece, right? If I make two arbitrary cuts, so you have an arbitrary piece of pie, and I say, now cut that piece into thirds, you might be able to do it quite approximately. You might have a method that'll get you close, but it wouldn't be a method that satisfies the rules of Euclidean geometric construction. So that kind of goes to the point that, in a way, maybe there are no unsolvable problems. Maybe all problems are solvable if you're prepared to think about them, think outside the box a little bit, right? Like Jace did with his, fill the glass and leave it empty. That's a good one.
Yeah.
That's like one of those little bar bets, right?
Oh, yeah.
Yeah.
Hey, old timer.
Okay, so there are methods to trisect the angle, but they're approximative methods.
Yeah.
Right? So methods where you can go through a process and get closer and closer. And actually, so I use one of these when I do cut pie. Right? So if I want to cut a pie into thirds, or more commonly into, say, 12 pieces, right? At some point you've got to divide something into 3. And it's kind of tricky. Like, you can always eyeball half, right? But when you try to cut something in thirds, usually you do the first cut, and then you do the second cut, and you realize, oh, that first cut, that was way too small or way too big.
What if you put a pie right on its side on a stick that rotated at a very specific speed? Okay, and you make a cut in one cut in the pie, and then you got this thing that's rotating at a specific speed.
It takes 30 seconds to travel
It takes
back.
30 seconds to travel, and then you stop it again on 10 seconds, and you cut it again.
Well, that's a very interesting method, yeah. So you could just stick one right on the turntable there. Yeah, but that goes quite quick, so you have to...
Can you try it on that turntable now?
Like a ninja. You'd have to be like...
Yeah, but then you could sort of time it and stop it. I'm just thinking, you could use time to help you solve the problem.
Yeah, that's a good idea. That's interesting.
Good idea.
Well, I have a solution that doesn't require a turntable.
Oh, right, okay.
Okay, it's pie time!
Pie time! Pie time for pie time.
Is there any way we can sort of shoot this from above? Is it possible? Does it just pop off real quick?
There we go.
Right. So here's your sort of think it of life hack, right? When you want to cut something in thirds, there's a technique, right? The technique is this. So
You heard it here first, folks.
you heard it here first.
Life hacks.
All right. So first of all, we're gonna sort of mentally. Now I would do this all just with my eyeballs, but so that you can see what I'm doing, I'll make
Use a
some
knife,
marks.
for God's sake.
I'll make some marks, right? Oh, you can't even really see the marks, can you? Okay. So first of all, let's make a line that divides our pie in half, right? Okay, so now we've got half of a pie over here. What we want to do is we want to get to a third of a pie. Actually, I can get down lower here. All right, so we've got half. Now let's take away a quarter. That's easy to eyeball. And now let's put back an eighth. And now we take away a 16th. We put back a 32nd. We take away a 64th. We put back a 128th. And now I'm just barely moving, so it doesn't really matter, does it? Because we're just looking for a practical solution.
Yeah.
So I make my cut right here, and that's 1/3.
Ah.
So that's it.
Before your very eyes.
Before your very eyes. So that's a little trick you can use to estimate a third of anything. Works for line segments. It works for, if you've got a quarter of a pie, you can divide that into 12ths.
Okay.
And then, okay, so I've done that one cut, and now if I want to finish the whole thing and put it all into thirds, that's easy, because now I just have to divide right down the middle between the two cuts. And so now I've got the pie cut into 3 pieces, which is great because Gavin's a vegetarian.
Yeah.
So there are 3 of us to eat the pie.
And he's what's in that
Practical
pie?
solutions.
It's a practical solution, yeah.
Yeah. Well,
That's because you won't eat any of that pie.
won't eat buffalo, will you?
Yeah, we've had to cut
Because
it
if it
into
was
thirds.
quarters, it'd be very easy.
Yeah,
Yeah, it'd be too easy to do in quarters.
yeah.
So there's your little life hack: how to cut something in thirds. And now, I find that sort of mathematically mysterious. Like, why is it that you can cut something in thirds by first going halves and then quarters and then eighths and then sixteenths? None of those things are multiples of 3,
No.
right? And yet at the end, in the limit, if you go on forever and ever, you end up with 1/3. It just seems mysterious to me. Like it's just a happy
You
coincidence.
will end up with 1/3.
Yeah,
Right.
yeah, you will.
Not near. You can actually get to an exact third by going on.
Yeah, okay, you'll never actually get there, but the longer you go, the closer you get,
Yeah.
right?
So you're actually less than the width of the knife.
Or if you really wanted a solution to get to a third in finite time, what you could do is you've got, say, maybe a minute to do your cuts, right? Do the first cut after 30 seconds. Do the second cut after 45 seconds. Do the third cut 12 and a half seconds later.
Yeah.
Do the next cut 6 1/4 seconds later, so that you're cutting faster and faster, and by the time a minute has passed, you've done infinitely many cuts.
Okay.
So now you're at exactly 1/3.
Okay. Right.
There you go.
But
So
you need to be the Flash to do that.
yes,
Yeah.
you'd have to be that.
The Flash is very fair when he's handing out pie.
Though actually, you don't really have to be that fast because with each move, right, you don't actually have to make those cuts. You're just moving the knife to find the place, right?
Yeah.
And each move gets smaller, so it gets easier and easier to do it quickly.
Wow.
Wow. So there's an unsolvable problem solved.
Wow. Well,
In a sense.
there you
Just as
go.
long as you're infinitely
You guys want some
fast.
pie?
Oh yeah, after all that.
I'm going to go ahead and cut it in 6 because these thirds are rather large.
You have a sixth of a
But
pie.
it turns out that there's a reason why that trick works, and it's kind of another trick, right? Because the process of starting with a half, taking away a quarter, putting back an eighth, taking away a 16th, that's an infinite series, right? It's 1/2 to the first power, minus 1/2 to the second power, plus 1/2 to the third power, minus 1/2 to the fourth power, on and on forever. And it turns out that if you write that down,
Yeah.
right, and then subtract half of it, you get an equation that you can quickly solve to prove that the result is 1/3. I won't write it on the board. Maybe I'll do a little
Have you done a
supplement.
paper on that? You should do a paper on that.
Oh, that's not worthy of a paper. It's common knowledge from university calculus, maybe even some high school algebra classes. But I doubt that
Integration or differentiation?
What's that?
Is it integration or
it's
differentiation?
neither actually. It's
Well,
an infinite
if you
series.
think about it, if you think about the number 12, if something's 12,
Yeah.
you cut it in half,
Yeah. That's
and then so you've got that half, and then you cut that half
half.
in half. That's 3,
Yeah.
and then if you cut that half in half again,
That's 1.5.
well, yeah, you keep going, you'll get it down to so you
Three
end up
quarters.
with 4 eventually. As you keep going again,
Started off
you
well, I
get
was
closer.
thinking- yeah.
As you get 1.5, and then you and
Yeah.
then you take a bit more off that.
Yeah.
So you take 3/4 off that, and then you. And
That's a
then
nice
eventually-
looking pie. Now, yes. Well,
Genuine buffalo, ladies and gentlemen.
oh,
I think
buffalo.
it's buffalo from Buffalo.
Oh, well, there you go. Well, that was the interesting thing because I didn't read that paper you sent me.
Yeah.
I didn't have time. Did you read it?
I kind of skipped to the end.
Did it make? Oh, so listen. Well, no. While we were just discussing this the other day, we were talking about unsolvable problems. Matt said, "Oh, unsolvable problems. That'd be a good thing to discuss." I went, "Oh, okay. Don't know anything about unsolvable problems." So we looked it up on the internet and we came across this guy called William Rappaport. Now he wrote a paper on unsolvable problems, which I failed to read. Matt has had a look at.
Yeah,
But
I've had a look at
what in the process, and he wrote on the importance of unsolvable problems in philosophy. But in the process, we discovered that he'd also written a sentence. Well, not only that, a sentence that incorporated the word buffalo, I think 9 times.
Was it 9? Oh. Did you not get some pie yet?
Yeah, you have that pie.
You have that one. You have that one.
No, that's got more. That's more of a pie. I've got only a little bit.
You have a napkin as well.
We've got pie. We've got wine. We've got Buffalo.
Great show.
Buffalo Bill.
Thank
So
you.
Buffalo Bill Rappaport I was immediately entranced by, because not only was he the major contributor to the I Love Lucy Memorial Museum, which I, obviously a major fan, because he's dedicated a lot of his hard-earned money to that cause, but he wrote a sentence, and the sentence is buffalo, 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 buffalo. Is that right?
That's exactly right.
That's right.
That's right.
So it's buffalo, 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 buffalo. It's 8 buffaloes in a sentence.
And it's a grammatical sentence.
It's a grammatical sentence that makes sense. So, yeah.
Okay, if you can believe it.
If you can believe it.
Maybe the unsolvable problem there is making sense of that sentence.
Yeah.
But it's not unsolvable because.
It's not a problem. It's
and sorry, folks, this is a bit of a tangent from the unsolvable
So
problem.
is that because buffalo's got different meanings?
Yes, buffalo's got 3 different meanings.
I see.
It's buffalo the place, buffalo the bison-like creature, and buffalo, which is the verb to bamboozle.
Which I did not know. Are we sure that old Buffalo Bill didn't make that up?
No, that's you get buffaloed by somebody.
I can imagine
buffaloed.
saying, "I've been buffaloed," or "I'm buffaloed." That's it. I'm buffaloed. That would be
So I
it.
presume you'd have to start with the place. So it's buffalo, buffalo. So it's buffalo that's in buffalo.
Yeah.
And then the verb. So they do that. Then
The
to other buffalo.
Brackets that buffalo, buffalo, other buffalo from buffalo.
So
Yeah.
it's the same grammar as Cincinnati mice, Cincinnati cats chase.
Chase
Cincinnati
cats.
That's it.
Yeah.
So
So you have to sort of
buffalo, buffalo,
drop the-
buffalo, 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 buffalo.
in the sense of buffalo from buffalo. What buffalo from buffalo? Buffalo. Also buffalo.
Buffalo, buffalo.
Buffalo.
Yeah.
Buffalo.
And that's actually very. Turning it to Cincinnati cats chasing makes complete sense.
Yeah, it's amazing.
So there you go. That's Buffalo Bill, who's obviously, well, we called it Buffalo Bill. I'm sure he doesn't refer to himself like that.
No, but I'm sure somebody must have.
Somebody must
the
have.
The man taught in Buffalo, New York, right?
And the man loves
Yeah.
Buffalo because he also published a paper on the best, a guide to the best restaurants in Buffalo. So he's Buffalo to the core.
Yes. So I don't know if there are any Buffalo restaurants that serve buffalo.
Oh, there must be.
There must be at least.
There ought to be.
Anyway, so but the sort of the gist of his paper, because he was talking about unsolvable problems in philosophy, and the question was whether
Nice pie.
yeah, and the question was whether the great problems of philosophy are completely unsolvable, as if to suggest we should just give up, stop chattering about them, which a lot of philosophers have thought, strangely enough. So. For
Why
example,
waste your energy
right.
on unsolvable
Yeah,
problems?
right, exactly.
Yeah.
So, for example, he talked about, what was it, the problem of free will, which personally I don't think is really an unsolvable problem. But that's because, I put myself in one of the camps that, that
when you
believe
say
in a particular solution.
so, what is the problem of free will being? Just to recap.
So the problem of free will is basically, it seems that the laws of physics are deterministic. Or in any case, at one point in history, it did seem that the laws of physics are deterministic, right? So the state of the universe before you were born already determines what's going to happen in your life, inclling everything that you're going to do, because you're just another physical object determined by physical laws.
A cog in the big.
In the big
Great
machine,
wheel.
right? Okay, and yet it feels like we have free will. We have freedom to choose. So that's basically the problem of free will. How can those both be true, or is one of those things an illusion? Is it the case that the world is not really deterministic, or is it the case that we don't really have free will? It's just an illusion, and actually we're just machines that think that we have a choice in matters.
And he's saying that that's unsolvable. So
Yeah.
let's stop thinking about it.
Well, Rappaport is not saying that. He's saying that this is one of those classic problems that some people regard as unsolvable. And he talks a lot about a paper by Benson Mates. Mates thought that this is an unsolvable problem.
Oh, that could be Buffalo
Could be
Bill
Buffalo
now.
Bill talking, yeah.
So actually, that's our little reminder to check on social media and see if anybody has
No questions. No questions. So far.
Everyone's obviously too wrapped with interest.
They've all got hungry and gone to have pie.
Well, they're asking for recipe tips.
Well, when you open with geometry,
Sai
you
is
can't really
here.
expect.
Sai is
big
looking at the pie.
audience. Oh, I'll bet she is. So he wasn't saying these problems are unsolvable. He's saying that, well, look, it seems like they're unsolvable because on Benson-Mates theory, the idea is that there are lots of proposed solutions, but each proposed solution requires you to accept some background theory. And there are always some background theory that not everybody is willing to accept. Maybe that most people are not willing to accept. And Rappaport thinks, well, okay, so that doesn't mean they're unsolvable in principle. That just means that there's some practical boundary to solving them. And in order to solve these problems, we're going to have to make some sacrifices and change our background way of thinking. So something like we might have to change the idea that the physical world is deterministic, or change our belief that we have free will. And by the way, just to talk about the free will problem, we now widely think that the physical laws are not deterministic because of quantum mechanics. We think that there's genuine randomness in quantum mechanics.
Right.
Right. Of course, there are some interpretations of quantum mechanics in which that's not true. But there's one sort of mainstream interpretation of quantum mechanics that says that the things these little particles do has a major factor of randomness in it. And it's genuine randomness. It's not just that we can't predict them, but they actually behave in a way that's uncontrolled by any sorts of physical laws. But it turns out that even if there's randomness in the world, that doesn't help solve the free will problem. Because now that means that instead of making choices, you're doing things randomly.
Yeah.
And that's not what it feels like either, right? It feels like we're making choices. We're not forced to do things, and we're not doing things out of complete randomness either. It feels like we're deciding what we want to do and willing to do it and making things happen. So randomness doesn't solve the free will problem. But the thing about Rappaport is he thinks, well, look, I love that line in the beginning of his paper, right, where he says, okay, so just because we haven't solved the problems doesn't mean that there isn't any progress in philosophy.
Right.
So it's as if to say, well, you're using an overly narrow concept of
the values in the
progress.
pursuits.
Yeah, exactly. It's one of those, the value is in the pursuits. Right?
Yeah, not in the results. Yeah, it's taking part, not winning.
Yeah.
That's
Everyone
philosophy.
gets a trophy. Everyone gets a trophy.
Yeah, we should have. This is what I was saying the
yeah.
other night. We should have a thinkative prize
Yeah.
that we award
Right.
for something like some sort of unsolvable problem, or something. We should have and it could be a pie. It could be nice wine, nice bottle of wine.
Yeah. Or a semi-nice bottle.
Or something not too pricey.
No,
something under
actually,
10.
this is really nice.
This is nice. This beefsteak.
It would be great with a
Argentinian
steak.
Melbourne.
It
And
goes great with a buffalo pie.
it does. It's gone well with a buffalo pie. But yeah, we are going to instate a thinkative prize.
Okay.
But
Maybe we should do some thinkative awards,
yeah,
like a yearly kind of roundup of
Yes,
the
we
latest
should.
things in philosophy and science.
we should.
A bit like the Darwin Award.
Yeah.
Like the Ig Nobel Prize.
And we could give people a pencil and a bottle of wine.
Yeah.
Yeah, right.
Sounds
Okay.
wonderful.
Now all we've got to
We'll
do
have
is
to do that.
think what those prizes will be.
Right.
So, any ideas for impressive pursuits in philosophy, or
Yeah.
then write in, and we will consider them for the thinkative prize.
That's
Yes.
right. So if you've got a problem that seems unsolvable,
Yeah, give that as well.
send it in,
Send it in.
and we'll see what we can.
We want
do.
your unsolvable problems, and then we can address
offer a
them.
prize for it.
Yeah, but we can also try and address them, because what are we if not a cutting-edge think tank?
Yes, indeed.
I would also be interested to see other solutions to the fill glass and leave it empty problem.
Yeah,
Okay, yeah, that's a good one.
That's
Yeah.
a good one.
yeah,
And
we're
I'm
ready.
sure there are other solutions. I'm sure there are
Oh,
other
there must be,
solutions.
Yeah, we're ready for you to do some work, listener.
Now, there are other sorts of unsolvable problems.
Yeah.
But again, these
Do
are
tell.
problems that have been proved unsolvable. So Alan Turing, right?
Mm.
You've all heard of Alan Turing.
Oh yeah.
Yeah, right.
Of course, yeah.
He's
Famous.
apparently become he's become a big hero of this country, right? And there's been films about him and whatnot, and lots of biographies. So the most important thing that he proved in his career, the most important thing that to my mind, the most important accomplishment was this paper that he wrote in 1936, in which he proved that certain problems in mathematics are unsolvable, and in particular, there's a problem to sort of have a general systematic method to solve all mathematical problems, right? So I think that was Hilbert's and Scheiding's problem, right? And he proved that it's not possible by proving that a specific problem is not amenable to any systematic solution. Now, the problem that he proved was unsolvable is called the halting problem. And this is a problem about computers, or about computer programs, but it's really a problem about recipes or methods, right? So basically what it is he proved that there's no method or computer program to figure out which methods and computer programs work and which ones don't. So this is actually kind of interesting for industry, because you might think that people who do software development would try to develop some kind of program that would look at their computer programs and figure out whether they work or not.
Yes.
That would be really useful if we could do that.
It sort of almost seems like something that would happen.
That exists.
Yeah.
That exists, yeah.
Well, thank you, sir. Yeah, but it doesn't. It doesn't
Why?
exist. And why? Because it's impossible.
Okay.
Absolutely impossible. Cannot be done.
Is it definitely impossible, or just thought to be impossible?
There's a proof that it's impossible.
Okay.
Now let me just say there, while I have great faith in mathematical proofs that they prove what they prove, one of my favorite philosophers said something very deep about this. Right? Imre Lakatos, who used to work at the London School of Economics, once said that certainty, and he was speaking specifically of mathematics, certainty, far from being a sign of success, is only a symptom of a lack of imagination. So, and he was speaking about mathematics generally. Whenever we prove something and we think that we're certain that it's true, that is a sign that we haven't thought outside the box. That we're not thinking broadly enough or using our imaginations to the widest possible extent.
It's about that thing about getting locked into reality tunnels again, really, isn't it?
Yeah, it's about like that, right? But it's kind of deeper because gosh, mathematics. Surely mathematics is supposed to be the paradigm of certainty. That's what's supposed to make maths different from. I'm saying maths now. Maths different from the other sciences, right? The empirical sciences.
Yeah.
Right, and the empirical sciences we observe, we concoct theories. We confirm them or we refute them, and we make generalizations that they're probably true based on what we've seen. But with mathematics, we have proofs, and things are supposed to be definitely certain. According to Lakatos, well, the problem is that the concepts that we use in mathematics are they have little sort of open areas in them, right? So like you might think what a polyhedron is, or what a polygon is.
And it could be any number.
Well, so I mean like shapes, right?
Yeah.
So you might think that I know, that like
an octahedron, for example.
Yeah, for example, right? An octahedron. Okay, 1, 2, 3, 4, 5, 6, 7, 8. That's a terrible octahedron.
Yeah.
Oh my gosh, we only have 5 minutes left. Is that true? No, that's.
No.
Oh, I pressed snooze. That was
nice. Wake up.
Right. So that's an example of a polyhedron. Of a polygon, right?
That's polygon. Yeah.
And you might think that you know exactly what a polygon is, and he actually mostly talks about polyhedra, which are like solid figures, right? So like like a cube, for example, is
It's got 6 faces.
Yeah, exactly. So that's a polyhedron. Okay, and you might think you know what a polyhedron is, but Lakatos shows you quite quickly that there are all kinds of things that seem to kind of fit your concept of a polyhedron, but seem to kind of not, and which violate the rules that you would expect polyhedron to follow, and things like that.
Oh, really?
So,
Okay.
So there's more room for imagination in mathematics than a lot of people have thought. But I do want to come back to the proof about computer programs and recipes and so on, right?
Yeah.
So the question is, how do you prove that there's no computer program that can inspect all the other all computer programs and tell whether or not they work?
Yeah.
Okay, so let's say that the criterion of a computer program working is that it eventually halts. And it comes to an end and it gives you your answer.
Yeah.
Right? So we're talking about programs that maybe compute the value of some function. Right? So suppose you've got a computer program now that can look at all the other computer programs, which all have to be finite length, right? The instructions have to be finite.
Okay.
So you give it any finite computer program and it'll tell you whether or not this program is going to halt. The reason that can't happen is very simple. Because if you had such a computer program, you could build another computer program out of it, right? Right. So now you have another computer program that just calls that master computer program testing program as a subroutine. And what you make this new computer program do is, given any other program, you run the master program testing program on it, and if the program says yes, this will halt, then just then go into a loop. And if the program says no, this won't halt, then halt and say no or whatever. So now you've got a program which, for any program you gives it, if that program halts, this one doesn't, and if that program doesn't halt, this one does.
So it's saying that basically computers can't analyze, computer programs can't analyze other computer programs.
Right, but I haven't got to the punchline yet. The reason that they can't is because now you apply this computer program to itself, and what it will tell you, and if this computer program that we've just constructed out of the master computer testing program, if you feed it to itself, right, then if that program halts, then it won't halt. And if it doesn't halt, then it will. And that's a contradiction. It's impossible.
Right.
So
that's why you can't do it.
That's why you can't do it. That's why it can't be done. So that proves that there's no computer program that can just look at any other computer program and tell you what it's going to do and what it's not going to do.
And we think computers are so clever.
They're clever enough, They
But
get us a
the
long way.
only reason they're clever is because they're created by the human mind. There's not a computer program. Is there a computer program, for example, that can create computer programs?
I believe there are. I don't know much about that, but surely there are computer programs that can create computer programs. There's just no perfect computer program testing program.
Okay.
And to me this is interesting, not because it's about computer programs, but because it's also about logic and reason and mathematics, right? Because when we do something in math class, we learn a specific method for doing it, which is just as good as a computer program. So what this shows us is that all the methods that we learn in school, they don't do everything. There are problems that they cannot solve. There are problems that cannot be solved with any sort of recipe or program or method. They cannot be done in a mechanistic way. And I can't remember now the name of the logician who used the term creative sets, because what he said, it may have been Emil Post, because what he said is these sorts of theorems, these unsolvable problem theorems, what they show us is that mathematics has to always be creative. We're never going to come up with a recipe that solves all the problems, so there's always going to be more work for mathematicians to do.
Cool. Well, that's good to be constantly, keeping yourself in work. I think that's quite handy, because you wouldn't want to be out of work. But okay, so I would love to see a list of unsolvable problems.
A list.
Do you think somebody's done a list of unsolvable problems? I'd like that. There's a book right there.
And have they read
Thinkative's book of unsolvable problems. There we go. There's
And
available for Christmas.
And have there ever been unsolvable problems that have thought, to be genuinely unsolvable, that we've actually been solved?
Oh, that's an interesting question. Have there been any problems that were thought unsolvable that have been solved? I mean, there have been many problems that resisted solution for a long time, right? Like Fermat's last theorem, right? And there are still problems.
Remind me of that one, please.
Oh, Jace, do you remember?
Oh, there's a whole Horizon program on. It's something I can't remember. It's something to do with. It's a number thing, but
Yeah,
it's
yeah.
finding a proof for a certain. I can't remember what
But it's since been proven that
A
it's,
guy called
you can-
Simon
it
Singer
has,
did it,
but
wasn't
it took a long time
Mm.
to prove it.
Just so okay.
Go on YouTube. There's a documentary about it.
Okay.
It was
Yeah.
in the 17th century or something like that, isn't it?
Yeah.
Fermat, right?
Yeah.
Mm.
Yeah.
Oh, Fermat, right? Okay, yes.
You know,
I'd always read it as Fermat.
Fermat.
Right.
French guy. Yeah, I know, but it's gone out of my head. I should have done it.
Okay, Fermat's okay, great. So yes, there have been ones that have been thought unprovable that have then since been proved.
Sure.
But with something as simple, to go back to the compass and the straight edge,
Yeah.
something as simple and basic as that, no, that is definitely unprovable, or am I just lacking mathematical imagination?
Well, that's I think the interesting philosophical question, right? Because they're definitely unsolvable if we have formulated them concretely and clearly enough, right? If we've been able to say what it means to do a construction with straight edges, means for it to be successful, in such a clear way that any solution is going to turn out to violate the rules, then it's unsolvable. But I think maybe someone like Imre Lakatos would say, oh look, you think that you've defined the problem so clearly that you can now prove it's unsolvable. But actually, your attempt to define the problem has holes in it that you're not noticing. So, and in a way, Jace's response is a good example, right? Because I didn't think at all about, the meaning of leaving
the
completely
line.
empty. Right?
Yeah.
I didn't think about that. I just that you understood pot, fill it to the top, and leave it completely empty. So now I could back up and I could say, all right, what I mean more precisely is make the glass full to the top and empty at the same time. Can you do that?
Yeah.
And you might say, okay, now we've got a completely unsolvable problem. There's no way anyone could come up with a solution to that. But, okay, wait a minute. What if we take the glass, we put it in a sealed box, a light-proof box, with a radioactive device and a mechanism and a cat, right? And maybe, according to some interpretation of quantum mechanics, that wine will be in a
Well, the cat will be drunk.
the cat.
Well, it can't be drunk or sober.
The cat will be in a superimposed state, of drunk and sober.
Oh.
Right? Oh, but maybe we could construct some kind of a quantum device so that the glass is in a superposed state of full and empty.
It's Schrodinger's glass, simultaneously
Schrodinger's glass
half
of what?
full and half empty.
Yeah, it's Schrodinger's moderate optimist glass.
Yes. And that's Fermat's last theorem.
Oh yeah.
Oh.
Right.
It's
So
any number above 2, I believe, xn plus yn equals zn.
right for any n above 2, right?
Yeah.
Okay. So it's to find solutions to the equation. These are integer solutions, right?
Yes.
So x, y, and z, as you say, all have to be integers, and n has to be an integer, and find an n greater than 2 for which there's a solution. We know of solutions where n is equal to 2, but Andrew Wiles proved then that there aren't any where n is larger than 2. So there's no solution to x cubed plus y cubed equals z cubed. No solution to x to the 4th plus y to the 4th.
Oh, really?
Right. So that's if I remember right. That's
Well,
what the
any
theorem says.
number. So say you got 2 cubed plus 5 cubed. There's no number that it'll.
There's no whole number for z that's going to be there's going to be z cubed. Right.
But
And
that has been proven.
that has been proved. Yeah, that was proved something like 10 years ago, and it was asserted in the margins of a book by Pierre de Fermat in 17th century or something.
And everybody had poo-pooed
and he
it.
said he even wrote sort of like in Donald Trump fashion, I have a proof of this, but it's too long for this margin. And if he did have a proof, then it died with him. until
Aw.
Andrew Wiles came around.
There you go.
Oh, that's sad that he solved it and everybody just went, yeah, like hell you have. And he had, didn't it?
Well,
Oh,
maybe
we don't know.
We
if he
don't
had.
know if he had or not. I rather doubt
Oh.
it because, well, you know, the stuff that Wiles pulled in was some quite sophisticated modern mathematics that Fermat wouldn't have had. So it's hard to see. It's easy to see how Fermat might have thought he had a proof of
Yeah.
it. But you know, I've written a few proofs of things, and what I find is thinking you have a proof and writing it down are two very, very different things. It's when you start writing things down, and the same goes for philosophical papers. It's when you start writing things down that then you start to see things that you didn't see before.
Yeah, it's like in this documentary about it. Some guys actually thought they had a proof, and they were very excited. And then some other mathematician said, they picked it apart and said, no, your maths are, and these guys were like, oh no, my life's work is like, I'm an idiot. Page 34 of my proof, I've done the wrong calculation. and it's
Schoolboy
all-
error.
It's all, yeah.
Yeah, and it's happened to the best, you know. These mistakes. Poincaré, Henri Poincaré was a 19th century mathematician and theoretical physicist who was given a problem to solve what's called the three-body problem. Right? Now, in Newtonian physics, if you've got just two bodies or particles that are attracted by gravity, and they're just in empty space, and they're gonna, you know, there are different things they could do, but sort of typically they just sort of revolve around each other, and they revolve in ellipses, and the ellipses are very calculable. These are very solvable problems, right? So if you know the initial, if you know the positions and the speeds of these two particles at some time, then you can calculate where they're going to be at any time. Right? So that's why you know, astronomers can predict the motion of the planets so well. Though even the motion of the planets is quite tricky, because it turns out that that's very, very easy when you have two bodies. When you throw in a third body, say like the sun and the earth and the moon, then the problem becomes considerably more complex. And there was this mathematical prize, right? Another prize. There was a mathematical prize problem to solve, to write the equations to predict the motions of three particles attracting each other gravitationally.
Okay.
Right? And Poincaré thought that he had a solution, or at least a big step towards this, towards the solution to this problem. But and he won the prize. But one of the guys who was just copy editing his paper for publication, you know, going through to make sure the spelling's correct and all right, he was a mathematician and he spotted a problem, and he wrote a letter to Poincaré, and Poincaré worked on it for a while, and he realized that his whole solution was wrong.
No.
His whole solution was wrong, and what he then submitted, and still they gave him the prize, mostly to save face, I think.
Okay.
And though they had to retract the journal, they had already printed copies of the journal, and the publisher Mittag Leffler had to go around and sort of gather them up and destroy them.
Oh,
Yeah.
that'd be good to get one of those.
Yeah, I'd love to see. There's one of them. There's a copy still at the Mittag Leffler Institute in, I think, Stockholm or something like that, somewhere in Sweden or Norway. But what Poincaré did then is he instead gave a proof of a result that seemed to show that these sorts of problems are in some sense unsolvable. Right? And for a long time, people have said that Poincaré proved that these problems are unsolvable. So that there's no solution to the three-body problem. If you're trying to compute, in particular, there's a problem about the stability of three bodies. So if you've got like three particles sort of moving around in space, and I say particles because, you know, they're supposed to model planets, but they're modeled as point-like particles, right? So they're attracting each other, and they're sort of going around each other in different ways. And what you want to know is, when they're going around and around, will one of these ever just shoot off to infinity? It could happen.
Right.
So how do you predict it? And people said that Poincaré proved it was impossible, proved that it was an unsolvable problem. But the problem was that when Poincaré did that,
he proved it was an unsolvable problem, or he proved that it couldn't happen.
he proved that it was he did neither actually.
Right.
He proved that there's something special about this. Two bodies are easy. You throw in a third body, and you get a problem that's called non-integrable. You can't solve it by the usual methods. But he didn't strictly prove that it was unsolvable altogether. And you had people, physicists in the 80s even, saying, and here's the three-body problem we know is uncomputable. You can't, or the stability problem for three bodies is undecidable. You can't prove that this sort of problem, you can't solve this kind of problem with an algorithm or a computer program. But that hadn't really been proven, and the problem was that only sort of since the 80s have we really developed a good theory of what it means for these kinds of problems to be unsolvable. And now we know more about it, but you have to be very, very careful when you throw around words like unsolvable, because you think you know what you're saying, and then, because, for example, Turing knows what it means. Turing knew what it means for a problem like Fermat's last theorem to be unsolvable, or a problem like the halting problem to be unsolvable, where all you've got are whole numbers and discrete symbols and nice concrete finite things like that. But when you're talking about points moving around in a continuous space, the rules change completely, and the question of what problems are solvable and what aren't takes on a whole different meaning.
It just occurred to me that a lot of what we've talked about in the past, like there are a lot of questions outside of maths, because maths you've got the certainty, but there are an awful lot of questions which are essentially unsolvable.
Like?
Well, like you said, free will.
Maybe.
I mean,
or the question of like
God.
Or why is there something rather than nothing? One of
Yeah.
my favorites.
Another unsolvable problem.
Well, that's the thing about that problem, is that a lot of philosophers have said it's unsolvable, or it's nonsense, we can never know. But for problems like that, there's no proof, right? With Turing's unsolvability of the halting problem, with results about the stability problem for planetary systems, we have mathematical proofs that say, no, there is no solution of this particular kind. So if you want a kind of solution, you're going to have to look elsewhere. But with problems like free will, the mind-body problem, why is there something rather than nothing, we might think they're unsolvable, but there's no proof. And my feeling is that philosophers of the 20th century especially have worked really hard to try to get people to stop thinking about those problems, because 20th century Western philosophers, especially English and American logical positivists, thought those problems are not real problems, they're unsolvable, and we should stop bothering with them. And I think that's wrong. We don't even have a proof that they're unsolvable, and even if we did have a proof they're unsolvable, there would be room to question that.
So the quest is for the proof of the unsolvability of any given.
Yeah, when you get an unsolvability proof, then you've learned something, right? Then you've learned, okay, don't look here, all right? Don't look for that kind of solution. We know that kind of solution doesn't exist. Look for a different kind of solution. You go Jason on it, and instead of trying to find a way to tip the bottle so that it will fill the glass and not fill it at the same time, step back, reinterpret the problem, take a whole new approach.
And leave the glass empty. Yeah.
Well, you did fill my glass, and
Now it's empty.
Now we're going to leave
Now it's
it
empty.
completely empty.
We've come full circle.
It's all about the
Problem
quest
solved.
to get to the
Problem solved.
bottom of the glass. Yeah. Well,
There we go.
I think we've solved
We've
it.
solved the problem.
We've solved the, well, we've
And we've had
understood.
some pie.
Yeah, we've had pie, and there's still some pie left.
But there's one thing left to do. Place up.
Okay.
We're doing E for sure this time.
E.
One. Yeah, E.
Yeah.
1, 2, 3.